Here's my setup that I'm going to use for this test. Um, I've got a gerbil controller hooked up. On this end here is a NEMA 17 stepper motor. This is actually more accurate than your typical stepper motor. It does um, 400 steps per revolution. A normal stepper does 200 steps per revolution in native stepping mode. I've got it hooked up to a ball screw that's mounted to this aluminum bracket that's mounted onto a linear rail. I've got an analog dial indicator that's mounted to the ball screw mount. So this is going to give us just general ball screw position. Um, the um, the aluminum L bracket is going to be contacting this piece of spring steel. This is a scraper actually, but it's nice and springy, which is what I want. And as you drive into this spring steel, this black digital dial indicator is going to show exactly how much deflection that we get. Um, and that is not the best. The spring in this black one is really not the best. So the idea here is I can go ahead and move this into this. This is free to deflect wherever it wants, but it will spring back to the original position. And for my continuity probing, here on the aluminum plate, I've got my ground connection, and then attached to this block here, I've got my probe signal connection. And the isolation the between these surfaces is really provided by the lubrication and the ball bearings in the linear rail there. So it's not the. I had another setup that I did with these 6 millimeter pins, and these are electrically isolated with this piece of Delrin that's been bored out, and then I can connect the sensor wire to this spring that's coupled to the 6 millimeter pin. But this didn't work for this particular setup, so I didn't use it. But anyway, we'll go ahead and drive this. We'll drive this into this surface. We'll detect the contact, and then we'll compare the overshoot depending on the acceleration settings, as well as the seeking feed rate for the probing routine. So I want to do, so this is the probing command, G38.3. I'm going to move it in the Y plus direction 5 millimeters, and the feed rate is 50 millimeters per minute. So here we go. Okay. So what this here is telling me is the machine coordinates where the probe indicated the contact. So essentially, when an electrical connection was made between the moving plate and the flexible plate, the machine position was 67.407 millimeters. And if I just take a glimpse at the current machine position, it's a tenth of a millimeter more than that. So I will go ahead and back off, and then we're going to do the same command, but we're going to double the feed rate and see what happens. Here we go. Okay, so here we got 67.42, which is 2/100 of a millimeter difference, roughly. Actually, 0.013 difference. But if we look at our machine position, we are, let's see, according to gerbil, were these two numbers subtracted from each other. So what is that? 260. My dial indicator seems to be indicating that we're point or 157 hundredths. So we'll back it off again. Now I can't watch everything, so there may be things that move, and I'll have to review that as I continue the testing. All right, so now we're gonna double the feed rate again to 200 millimeters per minute. All right, and we can see on the dial indicator right away, we can see it's over a half a millimeter of over travel. And in the DRO, that's about the same. So that actually checks out pretty good. We'll go ahead and back up. Okay. And then we're going to do another one. We'll double it again. 400 millimeters. Here we go. Hopefully nothing pops. All right. Now look at that. That's like 2.5 millimeters. And we'll see. Let's see. Now the good news is we're really roughly in the same place. So 67.426, and our first contact was 67.475. Now something probably moved at this point, but 67.475 versus 67.426. That's actually more than that's more accuracy than I'm able to either measure or move. The ball screw has at least 0.02 of a millimeter of backlash, and the stepper, I have to do the calculation on the actual accuracy of the stepping motion. I'll do that and put it in the text when I edit the video. But that contact point is really good, is really accurate. The problem is if you drive your tool 2.6 millimeters into your work, you're going to have a problem. So this method is perhaps accurate, but it is definitely not what you want to do. You don't want to drive it that hard into the work. Now, let's see here. I'm going to go ahead and move my window around a little bit. And I'm going to show you the setting the setting that's probably most important here. This setting right here. So this is your acceleration setting, and this is in millimeters per second squared. So millimeters times it's an acceleration parameter. Anyway, so if I increase this to 100, we're going to see a different behavior, assuming my stepper motor can handle this. We'll go ahead and move this back up here. I'm going to go ahead and adjust the black dial indicator. We'll go ahead and run our test again. Go back down to 50. Here we go. Okay, so I didn't see any movement at all on the dial indicator. And let's see, our probe, we got 68.952. If we look at our machine position, we're 69.027. So that's actually not that great. So we overshot. Oh no, that's not too bad. We overshot by a couple thousandths of an inch. All right, back off again. Okay, double it. Okay, so now we can see the black dial indicator registered something. And if we get a snapshot of their difference here, so we're 69.027 and we're 69.135. So we're about where we were on the initial 50 millimeter per second probe with the 10 millimeters per second squared. So increasing the acceleration by a factor of 10 only allowed us to double our seek rate when we're doing this contact-based feeding. So we'll back off and we'll go ahead and do the 200. I think I need to re-zero that black one. All right, here we go. Okay. So we're showing a 5/100ths on the dial indicator. And we got 68.82. I did change the pressure on the plate a little bit. We're about 4/10 of a millimeter, 3/10 of a millimeter deflection at the 200 speed. So let's pull that back again. We'll go ahead and run the 400. All right, now we're a 1/2 millimeter on the dial indicator, and Gerbil's telling us we're about 8/100ths of overshoot, which is pretty bad. Okay, so I'll go back. So we'll see if we can make our acceleration even better. I've never tried this before. I'll go ahead and double it again, or factor of 10 it again. Save that. We'll go back down to our 50, see what happens. Okay. So we're showing 4/100ths on the dial indicator and about 8 on the gerbil display. That actually seems worse than our second attempt. So we'll try 100 next. Okay, I didn't re-zero the black one. It moved about I want to say about 6/100ths. And actually this looks better. We're about the same, so we're showing about, roughly 6/100ths on the gerbil's perspective here. I'll back it off. We'll go to 200. All right, so we got 2/10, and gerbil's indication is about 3/10. So that's quite a bit. Okay, final test. This probably won't even run. We'll try it. All right, it did. And about a 1/2 millimeter overshoot. not really practical. And the reason it's not practical is the acceleration rate of your stepper motor is really driven by how much torque it can generate, but also the weight of the internals of the stepper have an impact. So there's an upper bound on how fast you can actually accelerate a stepper. You can't just get a bigger and bigger and bigger stepper motor and then infinitely increase your acceleration. So, you know, practically, I don't think I've been able to have a machine configured with much more than 100 and I want to say 150 millimeters per second squared acceleration. So the problem, I'll just demonstrate it really quickly. While with this acceleration rate and this small stepper, I can drive this thing at 400 millimeters per minute. But as I increase this, let's say to 800, it you can see what happens. The motor tries to accelerate very rapidly, and it just can't. So it doesn't do anything. So 600, that's probably missing steps. Doesn't sound good. 50. Still, that's not a good sound for that particular stepper motor. So that's the issue with trying to change the acceleration curve because you're overshooting and you're trying to probe. Now, if you can keep it really slow, then you don't have much of a problem as you've seen here. But feeding at 50 millimeters per minute, that's not fast. And so if you're probing, let's say you're probing a large diameter circle or something like that. I mean, it's just if you're height scanning, this is going to take you forever. And so this is why this method, while it's very easy, all you need to do is make an electrical connection between your probe and your work. It's really less than ideal.